Hey, everybody. I wanted to, first of all, apologize that I can't make it to class this week, but I also wanted to provide you with at least a video of me going over the problems from 3.2 on the logistic equation. A few of these problems could be made a lot easier simply because of the fact that we have already derived in our lesson last week the formula, or rather the function that is modeled by the logistic differential equation. So I'll start off by just writing those up at the top so that we can see those, and then we'll refer back to those as we do each of these problems. All right, so recall that here we have the formula that is the logistic model for population growth typically, but remember that in general what that means is that if you've got some population over time, that the graph will start with an initial population at P0, and it will eventually increase, but then level out to a carrying capacity. And we should remember that that carrying capacity is going to be A over B. And we derived that, so look back to your notes on that. Okay, so I'll go ahead and write that up here. Recall that the carrying capacity for the logistic model is A over B, is when the population equals A over B. Okay, so in number one, and then we derived the formula for what that population function would actually be, and therefore this curve, P of T, is formed by this function. All right, so now we can use that fact in this next problem, where this one is interesting because it's not really a population of people, but it's a population of supermarkets in this case. So here we're saying that the rate of change, or the rate at which the number of supermarkets in the country uses a computerized checkout system is proportional to the number of supermarkets times this quantity right here. All right, now one thing to recognize is that implies that A is equal to 1, and it implies that B is equal to 0.0005. And that may be necessary for us coming up here shortly. And it says here to use the phase portrait model, or the phase portrait concept, to predict how many supermarkets are expected to adopt the new procedure. So that's where we need to now draw our phase portrait. Remember that in order to come up with our phase portrait here, okay, we simply need to set each factor equal to 0. So first of all, we find the critical numbers, which means where is n equal to 0, which obviously would mean that 0 is one of our critical points. And the second one is where is 1 minus 0.0005 n equal to 0. So that would be where 1 is equal to 0.0005 n. To get rid of the decimal, we could first of all just multiply both sides by 10,000. And that would give us that 10,000 is equal to 5n. So divide by 5, and we find out that our value of n is 2,000 divided by 5. All right, so that means that we've got another critical number at 2,000. So now based on our phase portrait, we just plug in values for P0, or rather I should say N0, that are above 2,000, that are somewhere in between 0 and 2,000, and somewhere below. Now, obviously, I'm not even going to bother with this one to pick something below because you can't have negative number of supermarkets. So why don't we go ahead and pick something like 1 right here, something between 0 and 2,000. Well, I would take 1 minus some small quantity, which would make that function or that quantity positive. 1 is positive, so that would mean that this would be a positive value, which means that this is going to be increasing. So the rate of change will be positive, which means that this function will be increasing as it passes through. So we should already recognize then that the value of 2000, since anything we pick between 0 and 2000 is going to have a positive slope, that means that it's going to increase, but then eventually level out to 2000. Okay. Now, if we pick something above 2000, like 10,000, notice that when we plug that in here, that's going to give a value that's bigger than 1, more specifically 5. So 1 minus 5 will be negative, which would mean that this is going to be decreasing, and therefore this is decreasing everywhere above 2000. So that means the 2000 is an attractor, so no matter either way, it's going to level out to 2000. And so let's just think about what that means. That's answering the question here. It says, predict how many supermarkets are expected to adopt a new procedure over a long period of time. So what we basically just shown is that as time goes to infinity, the number of supermarkets approaches 2000. So 2000 supermarkets eventually, over a long period of time, will adopt this computerized checkout system. All right. So now it says to, if the number of NFT of people in a community who are exposed to a particular advertisement is governed by the logistic equation. Now it's changed. I'm sorry, that's part number 2. Now it's saying solve the initial value problem and then use a graphing utility to verify the solution curve in part A. How many companies are expected to adopt the new technology when t equals 10? So this is where we now just have to use this model up here. Okay, we already recognize that if this is our differential equation, that looks exactly like this form. So it tells me that it's logistic, and therefore it means that we're going to be able to take the function p of t and solve. Okay. So we can now start plugging some quantities in. So let's start off with recognizing that A was equal to 1, B is 0.005, and since n of 0 is 1, that means that P0 is 1. So that means that we can say that we have everything we need. That means that P of t is equal to, well, 1 times 1, P0 times A, over 1 times 0.0005 plus, and now we take A, which is 1, minus P0, which is 1, times 0.0005. And that's going to be the coefficient of our exponential term, which is e to the power of negative 1t. So to simplify this just a bit, we end up getting P of t equals, sorry, give me 1 second here. Okay, so the numerator simply becomes 1. The denominator becomes 0.0005 plus, now we get 1 minus 0.0005, which is 0.99. Hold on, I'm taking away 0.005, so that's 0.9995. Okay, e to the negative t. Okay, and if we choose to try to simplify this just a little bit more, it might be helpful for us to multiply numerator and denominator by something that's going to simplify this. So why don't we rewrite this by multiplying the numerator and denominator just by something that's going to make this look a little cleaner. Okay, if I multiply the numerator and denominator, first of all, by 10,000, then that should eliminate the decimal. And instead of dealing with e to the negative t, why don't we just multiply by e to the positive t? because notice that e to the t times e to the negative t, right, is just e to the negative t plus t, which is e to the 0 or 1. So that's what's going to cancel out that negative exponent. And so that becomes p of t equals, well, in the numerator, we get 10,000 e to the t. The denominator, we get 5 plus 9,995. I'm sorry, we get 5e to the t, right? 10,000 times this gives 5 times e to the t plus 9,995. And the last step I'm going to do in order to simplify this is now just cancel out a 5, which has a common factor of 5 everywhere. And now we're left with 2,000 e to the t over, cancel out a 5, we're left with e to the t plus, and now we take 1 5 away from 10,000, and that gives me 1,999. And that would be a good model for this particular scenario, okay? But the last thing it asked me to do is to actually find what is P of 10 going to be. So we just simply need to plug in 10, and at this point I'm going to use Desmos. So here we have the graph, and at this point I would like to mention that we didn't technically need to get rid of the negative exponent. I think it is easier to work with if we don't have negative exponents in the problem. So that's why this model right here would be pretty good. And you can see that this model is, of course, a logistic curve. It has a carrying capacity of 2,000. And now all we're trying to do is figure out what's going to happen when we plug in 10. So we could actually just move along here and recognize that when I plug in 10, okay, that's going to be right over here at 10. Now let's try to scroll up until we get to 10. And therefore, it looks like there's going to be a total number of supermarkets of 1,834. Okay, and so here, instead of plugging it in and calculating it, we could just use Desmos and see that. Okay. So that takes care of number 1. So this gives us 1,834 supermarkets you can expect after a total of 10. Now, whatever 10 is, it doesn't indicate whether or not time is measured in years or months or whatever it is, but we do know that 10, whatever unit of time, is going to yield 1,834 supermarkets. So let's take a look at number 2. So now for number 2, it gives us a little bit of information, but N of T is now describing something different. So it's not describing the number of supermarkets that are using a computerized system anymore, or a computerized checkout system. Now what it's referring to is the number of people in a community who are exposed to a particular advertisement. And it says it's governed by a logistic equation. So if we just take a look back to Desmos, let's just think about what this is saying now. It's saying, I start with a certain number of people that have seen this advertisement. That's 500. So initially 500 people saw an advertisement. Maybe it was a commercial that aired during a certain show at 9 o'clock at night, okay? But then over time, more and more people would have seen it. So now maybe we're saying that 1 is the number of days. So now 1 day later, 1,000 people have seen it. And we're now recognizing that over time, if you just let that advertisement run over and over and over and over on this network, eventually 50,000 people will have seen it. Okay, so taking a look at this from a logistic equation perspective, we could see that it really starts off exponentially where a lot of people start seeing it. But then it starts to get to a point to where it'll level off because a lot of those same people are seeing the same commercial, so you're not going to count them again. You're only going to be counting new people that are seeing it, so maybe it's people that are just signing in for the first time, which is why it starts leveling out. And just pretend that this is now 50,000. So that's why you can expect that this would be a good model for this scenario. So now it's asking us to solve for N of T in this situation. So we just need to start recognizing what each of these values mean, okay? First of all, we should recognize that this is our P0. Okay, that's our initial population of people that have seen this advertisement. We've got to realize as well that 50,000 represents the carrying capacity. We recognize that the carrying capacity, we proved this already, so we don't have to prove it again, is that it's A over B, keeping in mind that our differential equation, okay, has the form, a logistic form of n times A minus Bn. So the values of A and B are what are going to govern this value of the carrying capacity, okay? So notice that what that also means is that the A value is going to be 50,000 times bigger than the B value, right? I just multiplied B over to the other side. So that'll be helpful to recognize, okay? And so we could already start to fill in this formula, because we know that N of T, which by the way, I just realized on number one, I shouldn't have been calling this N the whole time, or I shouldn't have been calling this P, right? All of these P's should actually be, just because of the fact that I had my original formula was N, it should have been N everywhere, which means that all of these should have also been N. N of T, N of T. Okay, so just to stay consistent with the naming of our function, okay, even though we're technically talking about a population. Okay, so N of T should be the initial population times A, so 500 times A, over, I'm sorry, this is sketching out a little bit, not wanting me to draw a straight line. Okay, over the initial population times B, okay, and that was a plus or minus? It was plus A minus B times that population, which is A minus 500B, times E to the negative AT. Okay. Now we could go ahead and use the other fact here, this initial condition. It's not an initial condition, but it's a condition that's told that after 1 week or after 1 day, 1,000 people have seen it. So that means that I could replace T with 1 and N with 1,000. So we can now replace our N with 1,000 and our T with 1, which would make it 500A in the numerator over 500B plus A minus 500B E to the negative A, where I just replace T with 1. So at this point, again, I'm gonna get rid of the negative exponent because I would rather not deal with it. So I'm going to multiply top and bottom by E to the power of A. And in doing so, that means that this is going to have E to the A. This E to the A cancels, and therefore I'm left over here also with E to the A. Okay. All right, well, at that point, we now can cross multiply and we get an equation with only A's and B's. Okay, so when we do that, that's going to become 1,000. I'm going to multiply this over to the left side. So that gives me 1,000 times 500 is 50,000. I'm sorry, it's 500,000. B E to the power of A plus 1,000A, 1,000A, and minus 500,000, 500,000 B, and all of that should equal the numerator, which is 500A E to the A. And that should do it. So we now have an equation with A's and B's. But remember, we also have another equation with A's and B's because we were told that the carrying capacity is 50,000. So that means that all of my A's can become 50,000 B. So I can actually replace each of my A's with 50,000 B. Right here, and finally right there. Okay, so we can now replace each of those and get an equation with only B's. Now you can see that there were 4 locations that I could have plugged in A. And if I did that, I would be changing each of these exponents to 50,000 B. And that would just seem like it's a much harder process to do. So why don't we reverse this then and maybe recognize that A equals 50,000 B also means that B is equal to A over 50,000. And now it's going to be a lot easier for us to plug in these quantities, right? Because now I just replace this quantity and I replace this quantity. And that's going to be much easier to do. So by plugging in A over 50,000 for each of the B's, we end up getting this form right here. And that made it a lot easier because notice 50,000 goes evenly into 500,000 10 times. And so I could cancel it out from here and from here, giving me this equation in purple down below. And so now notice that I've got a couple of A e to the A terms. And I also have a couple of A terms. And so why don't we go ahead and shift everything around here and factor, and maybe we can solve this. Okay, so if I were to combine 1,000A minus 10, that would give me 990A. If I were to subtract 500A e to the A from 10A e to the A, I get minus 490A e to the A. And that equals 0. And now notice that by factoring out an A, I mean, we could actually factor out a bit more than that. We could factor out a 10A. Okay, if I factor out 10A, I'm left with 99 minus 49 e to the power of A. And by the zero product property, I can now set each one separately equal to 0. So that means that A, one of the critical numbers, would be when A is equal to 0. The other critical number would be when this is equal to 0. So by solving this equation equal to 0, we subtract 99 and divide by negative 49. And now we take the natural log of both sides, and we get that the A value is the natural log of 99 over 49, which is approximately 0.7033. Now keep in mind that by using the original relationship between A and B up top, we know that B will be equal to that quantity divided by 50,000. So when we take that quantity and divide by 50,000, we end up getting 1.406. So that becomes 0.00014 or so. Okay, and that was simply by using this formula. So now we know A and B, which means we can go back to our original function, our logistic equation, and we just simply plug in our quantities for A and B. Here we go. So we can plug in each of those quantities, and this would be our actual function that models this scenario. Now, this was one big algebra problem trying to find A and B. I'm sure that we could simplify this a bit more, and I'm going to go ahead and try to do that just to make this look a little better without all the decimals. Maybe we could get rid of the decimals and make this look a little bit cleaner. So after we plug this in and simplify a little bit, this is the result that we end up getting, it looks like. Okay. And so that takes care of number 2. So obviously, you know, we're not really doing any solving of differential equations, because in deriving the general formula last week, we're really just now using that formula along with the information that we're given And so we're not really doing any integration anymore for these types of particular problems. So let's take a look at number 3. So in number 3, it now gives us another differential equation where A and B are given, right? So we have another logistic equation, P times the quantity A minus BP. Yet now it says that P is a population in a suburb of some large city, okay? And it's given by this initial value problem. So it tells me that 5,000 is the initial population. So we refer to that as P0. And so notice that if this is our model for the population, then we just plug everything into the appropriate spot. And now we can start simplifying. You should recognize that 10 to the negative 1 is 1/10. 10 to the negative 7 is 1 over 10 to the 7. So if I start simplifying each of these, we could just start canceling out some particular quantities. So when we realize that 10 to the negative 1 is 1/10 and 10 to the negative 7 is 1 over 10 to the 7th, then we could realize that 5,000 is 5 times 10 to the 3rd. So we could actually cancel that out to give 5 over 10 to the 4th, which is 0.00005. And then over here, same thing, you would just calculate this. This simplifies to be 0.0995. And of course, the numerator becomes 500. So there's our function. So when we're given our differential equation, we know what A and B are. When we're given an initial population, we know what P0 is. So it's just a matter of plugging it into our function and solving for, or simplifying. It now says at what time will the population be equal to 1/2 of its limiting value? 1/2 of its limiting value. Well, we first of all have to figure out what is the limiting value. Okay, so keep in mind that the carrying capacity, okay, the carrying capacity is A over B. Okay. So if the carrying capacity is A over B, then that's just 10 to the negative 1 over 10 to the negative 7, which is 10 to the positive 7 over 10 to the positive 1, or 10 to the 6th. So notice that the limiting value is 1 million. So if the limiting value is 1 million, that means that eventually in this large suburb, the suburb of this large city, eventually the population will approach 1 million people. So we want to know, when will it be half of that carrying capacity? So all we're doing is replacing P of T with half of 1 million, which is 500,000. Okay. So when we replace that with 500,000, we're now just trying to solve for the value of T. You can actually punch that function into Desmos and it'll tell you, you could use your graphing calculator. Obviously we could use algebra to solve this. I'm just going to allow you to do that work to make sure that you see to cross multiply and solve for T. But notice that the T value will become about 52.9 months. Okay, so over a long period of time, for a suburb that starts with 5,000 people, it'll get up to 500,000 people, 1,000 times more, in about 53 months, or a little over 4 years. But in the long run, then I would recognize that the population will approach 1 million people. So now for number 5, we should recognize that it's a slightly different differential equation, because it's now talking about a fish hatchery, which is essentially just an area in the ocean where fish are growing and not growing, but they are populating, and the population is increasing. And so this population would be increasing as a logistic model. But when we fish from a fish hatchery, we're also taking a certain number of fish per day, or a certain number of fish per unit of time. So what we want to make sure of is that this is sustainable and that we're not taking more than can be replenished. So for instance, if we know that 1,000 are being born per day, but we're fishing at 2,000 per day, eventually that population is going to become extinct. And so So notice that's why in a situation where we are constantly pulling a certain number of fish per unit of time, we'll subtract H. So it said to just assume that A, B, and H are these values over on the right. If we plug those in, this becomes the differential equation. Okay, so that's different than a standard logistic model. So it won't be the same function model that we had before. So the first one says to use a phase portrait concept to be able to find out what the limiting value is for this situation. So notice if we're going to do that, we're going to have to distribute here. This is going to give me 5p minus p squared minus 4, okay? Which would mean if we put this into quadratic form, that should be p squared, my apologies, negative p squared plus 5p minus 4. And now we have a quadratic trinomial, so we're trying to find out when that's equal to 0. So let's factor out the negative. We get p squared minus 5p plus 4. And now we get negative p minus 1 times p minus 4. Okay, so notice that these are going to be, when we solve dp dt is equal to this, that would mean when the population is equal to 1 or the population is equal to 4, those are going to be critical numbers. So let's put 1 and 4. Okay. And now if we, right, that's how we set it equal to 0, and that's how we found our critical numbers. So now let's just go ahead and pick some potential values for my population, which are going to be in each of these regions. So let's pick 0 and see what happens. By picking 0, this would become a negative times a negative times a negative, which is negative. If we pick 2, that would be a negative times a positive times a negative, which would mean positive. And finally, if we choose 5, that would become a negative times a positive, which is negative. All right. So it says that, well, we could see then that 4 will be technically an asymptote. And apparently 1 is technically an asymptote. But notice that as we go to infinity, we should recognize that if it's increasing here, that it's going to be getting close in this way. If it's decreasing, it's going to be getting close over here. And this one will just be decreasing forever. So we can see that 4 would be a horizontal asymptote for that population, okay? So now in the second part, it says determine the long-term behavior of the population in each case. So basically from this, we could just see that when the initial population starts higher than 4, or between 1 and 4, the population will approach 4, or I could say that the population approaches 4 as t approaches infinity, okay? If the population is somewhere between 0 and 1, right, which, because the population can't be negative, then I know that the population is just going to decrease to 0 towards a finite time, okay? And now the second part of this just says to solve this initial value problem, verify the results of your phase portrait by using the graphing utility and plot your information. So basically, we've got this differential equation, and now this is where we need to solve. So we can't just assume that it's the same population model because of the fact that we subtracted H. This is a different scenario. We're saying the population grows using this model, but the population decreases because we're pulling a certain number per day, okay? And so we've got to now solve this again. So obviously, in order to solve this differential equation, we would have to separate variables, which is what we did here. We divided by p minus 1 times p minus 4 dp. And now on the right side, we end up getting negative dt. I'm going to leave this as an exercise for you because we've solved differential equations in this form before. So this is just integrating by partial fractions, finding out the values of capital A and capital B. And when you simplify, you should get this function right here for your population. notice that all we've done is we've replaced our initial population. We just said that we replaced t with 0, and therefore the population would be p0, which is where we would end up getting this function right here. Okay, so once we get this, part C asks us to do something in addition to that. It says, use the information to determine whether the fishery population becomes extinct in finite time. So let's think about what that means. It says to find, if we want to find when the population becomes extinct, which is going to obviously be, be in the case between 0 and 1, then why don't we just set the population to become 0? So if we set the population here to be 0 and solve for t, we'll determine whether or not we get an infinity or we get an actual value. Okay, and if we get an actual value, then that would mean that it will in fact become extinct. Now, it won't become extinct, remember, it won't become extinct if the population is between 1 and 4, or if the population is greater than 4. It's only going to become extinct if the population begins between 0 and 1. So let's go ahead and solve that and finish this up. So when we want to solve this for when it's equal to 0, keep in mind that fractions are only equal to 0 when the numerator is equal to 0. And so the only time the denominator really matters is when we're trying to find out when it's undefined. Well, if I cross multiply, the denominator cancels anyway. So we can now solve by just setting the numerator equal to 0 and adding that quantity over. So we get 4 times p0 minus 1 is equal to p0 minus 4 times e to the negative 3t. Okay, dividing both sides gives us 4 times p0 minus 1 over p0 minus 4. That's going to equal e to the negative 3t, so I could take the natural log of both sides, which gives me negative 3t, divide by negative 3, and that gives me negative 1/3 times that natural log is equal to t. Okay, and so notice that don't worry, we don't have a variable on the left side, because we're saying that if the population begins between 0 and 1, we could find out the number of the amount of time that it's going to take to become extinct by just plugging that quantity in. And the time is going to differ depending on whether or not we start with, now when we talk about 0 to 1, we're not talking about necessarily one individual. Maybe we're talking about 1,000, and maybe each of these values are in thousands. So maybe this is 1,000 and 4,000. Okay. So if that's the case, it's not like, we're starting with half a fish. Okay. We're starting with somewhere between 0 and 100 or 0 and 1,000 or 0 and 1 million or whatever it is. Okay. But notice that at that point, the time will be dependent upon what the initial population was. And if we choose some value between 1 and infinity for the population, now we'd realize that this here does not go extinct. Okay, so that takes care of all of your everything for 3.2. What the last thing I want to mention is that next week we are going to be having an exam. I'd like you to. I know that it's also going to be the week that we return to school, which is exciting, and I don't know exactly what that's going to look like necessarily for our class. So I'll be in contact with you then. But I'd like you to determine a time that works best for all 8 of you for when we're going to be taking our exam the following week, okay? Which would be the week beginning the 22nd. So somewhere between the 22nd and the 26th, okay? I'm relatively open to when you choose to do so. But I want to come up with a time that we're going to be able to take that. So it's going to be on exact equations from 2.4. It's going to be on substitutions from 2.5. It'll have, there will be one logistic question on there from 3.2, and it'll be a little bit from 3.1, okay? The applications I give are going to be relatively straightforward, relatively simple. Don't stress yourself out on those. You are still going to be able to use your notes and your homework for those of you that actually do the homework. And so let me know a time that works. and we will see you next week. Bye-bye.